So now we want to take our new rule that we've learned for the general multiplication rule, and we want to apply it to a tree diagram just to make things really fun and interesting. So suppose that we have a shipment of 200 dishwashers to Sears from a manufacturer, and in that shipment there are 8 defective ones out of the 200. And you're working for Sears, and you're going to inspect 2 dishwashers at random and to see whether the shipment is okay or not. So the first thing we're going to do is we're going to construct a tree diagram of the sample space. And we're going to include probabilities for each of the branches and each outcome. And we're going to give both fractions and decimal places. We're going to let D be defective and F be fine. So not defective. So that'll work. Okay, so realize when we draw our first dishwasher, because we're going to draw 2 of these. When you draw your first one, you have 2 options, right? It could be a defective dishwasher or a fine dishwasher. So that means you're going to have a branch with a D and an F. Now, the chances of pulling a defective one, there are 8 defective ones out of 200. So the chances of pulling a defective one is 8 out of 200. The chances of pulling a fine one is 192 out of 200. And there we have it. Okay, so now let's look at the top part. We've already drawn a defective dishwasher. Our first dishwasher is pulled, right? And so we said we had a chance of doing this of 8 out of 200. Okay, well, now there's 1 dishwasher pulled. I've already pulled a defective one. That means there are 7 defectives left out of a batch of 199 because there aren't 200 dishwashers left. By the same token, there's still 192 good ones left because I haven't pulled a good one yet. So that means that leads to the first 2 outcomes possible. So you could say that you have a branch of 192 out of 199 for that top part. Right? So that leads you to your first conclusions. So you could have 192 out of 199 times 8 out of 200 for defective versus fine. Sorry, let me reverse that. So to go from defective to fine, you take 8 out of 200 because there were 8 defective ones out of the 200. Once you've pulled a defective one, then there's only 192 fine ones left. So that gives you 192 fine ones out of 199 left to draw. And when you multiply those, and I just use my calculator, 8 times 192, 200 times 199, and I divided the numerator by the denominator, and I get 0.0386. By the same token, defective would be I have an 8 out of 200 chance of pulling the first defective. Then once I'm after that first branch, I'm on the second branch. There's only 199 left. And out of those 199, 7 are defective. So that gives me a probability of defective of 8 out of 200 times 7 out of 199, which is about 0.0014. Again, you multiply the numerators and then multiply the denominators and divide. Okay, what if the first one I pulled was fine? Well, if the first one you pulled is fine, then you have 191 fine ones left, and you have 8 defective ones left. So that means that you have a chance here of pulling fine defective as 192 out of 200 times 8 over 199. There you go. And that gives you about 0.0386, same as this one, as a matter of fact. Defective fine and fine defective are the same probabilities. And then fine. Well, there's 192 fine ones and then 191 left after you've drawn a fine one already. So the second one is the probability of drawing another fine one given that you already drew a first one. And that's 191 times 199 after you've already drawn 192 out of 200. Now notice the tree diagram really helps us analyze what's happening. So the first draw we pull, it's out of 200. The next draw, it's going to be out of 199. It's a question of what you drew in the first bit, whether it was defective or fine, affecting what's left. And then you just multiply across, right? 8 times 7, and then 200 times 199. Or 192 times 191, and then 200 times 199, and so on. All right, now what's the probability that the first dishwasher is defective and the second one is fine? Well, that's this part right here. We already found it. Defective fine would be 8 out of 200 because you draw first one, it's defective. There's 8 defective ones. So 8 out of 200. The next one, well, there's only 199 left, but you're going to draw a fine one, and there's 192 perfectly okay ones in there. So it's 8 times 192 over 200 times 199. Or if you like, it's 0.0386. When I multiplied them myself, I got this number. So 1,536 over 3,009 or 39,800, excuse me. And there we go. Okay, so that's not bad. We already found that with the tree diagram. But that's a very different question than letter C. Letter C is, what's the probability that one dishwasher is defective and the other one is fine? Well, that's not saying the same thing. This, in problem part B, said the first one was defective. It was very clear. So it's saying make the first one defective. And this one's saying make one of them defective. That's not specifying which one. So it could be the first one's defective or the second one's defective. But there's the word or. That means that you're going to need to use the addition rule that we learned in section 5.2. We need the probability of df plus the probability of fd. That's because they're disjoint, right? You can either have the first be defective or the second be defective, but you can't be both and still have only one defective. So I need the probability that of df, which is 0.0386, plus the probability of fd, which is another 0.0386, convenient, which ends up being 0.0772 when you add those two up. So notice we're using the addition rule here. Let's make a note. For disjoint events, because these events were disjoint, right? You can either be df or you can be fd, but you can't be both at the same time. Now let's go back to one of our favorite friends, the probability of at least one. So what's the probability that at least one dishwasher will be defective and the whole shipment will be sent back? So they're going to send it back if anything's defective, and so if at least one of them are defective when you pull them. So you're going to draw two, right? Because it said so earlier up in the problem that we're only going to look at two dishwashers. So what I really want to know is what's the probability that at least one of those two dishwashers is defective? But we learned a while ago that the easiest way to do that is to take 1 minus the probability that none are defectives. So we get no defectives in either draw. Neither dishwasher is defective. Or how about this way? No defectives for either dishwasher. For either dishwasher. Okay, well, that's 1 minus the probability of, if they're not defective, that means that they're fine. So I want both of them to be fine. Right? I want 1 minus the probability that they're both okay. Well, that's equal to 1 minus, let's see, probability they're both okay is 0.9214. So that's what I'm going to use, approximately, which is approximately 0.0786. Which is a 7.86% chance. The chance that this shipment will be sent back. And there you go. Okay, so now that we've applied the general multiplication rule, and we've seen it multiple times, including in a lovely tree diagram to help organizing our thoughts, now we want to compare the two rules that we've learned here. Conditional probability versus the general multiplication rule. How can you tell which one's being asked? So let's read this problem. It says a math professor gives two tests to her Math 133 class. Imagine that. 65% of the class passed both the tests. So 65% of the students passed both one and the other, or first and second, I should say. And then 85% passed the first test. What percent of those students who passed the first test also passed the second? Okay. Percent of those is kind of a key word here. So we're talking about people that have passed the first test, or percent of those who passed the first test. I guess I should highlight all that. Also passed the second. So what I'm getting at is, what percentage passed that second test given that they already passed the first test. The given that isn't written out in words, but of course that's what was being highlighted right here, right? They've passed the first test. Percent of those who passed the first test. That's given that. Let me type that up one sec. So we have to analyze that language and realize what they're talking about. So they're saying, of those who passed the first test, of those that passed the first test, that's given that they passed the first test. What's the chance they pass the second? Okay, well, let's look at the rules up here. Now, we've used the N one, the number of ways. You can have E and F divided by the number of E, this part, multiple times. But this is one time where we're not going to because we weren't given N. We don't know how many students were in this class or anything. Instead, we're going to use this one. We want the probability of E and F divided by the probability of E. For us, it's going to be the probability of passing the first and second. So pass first and pass second divided by the probability that they pass the first. Remember, it's the first event that goes in the denominator, right? Because it's the thing that you have to assume is given. So given that they passed the first test, what's the chance they passed both of them? Well, both of these were given to you in the problem, right? It's a little hard to see, but they tell us that, oops, here, equals. They tell us that 65% pass both of them. Well, if that's the case, then that means that the numerator is 0.65. And then they tell us that 85% pass the first test, so 0.85 in the denominator. So let me highlight those parts for you. Here's the percent that pass both. That's your numerator. I'll make it a color. How about green? Right, there's your numerator. And then right there is the passing the first test. That's the denominator. That's the given that part, and I'll make that pink. Right? So you take that numerator, passing both, dividing by passing the first one, and you're going to get 65 over 85, which reduces down to 13 over 17, which is in a decimal about 0.7647. So given that they passed the first test, the chances that they pass both of them is about 76.47%. All right. Now, a math professor gives 2 tests to her Math 154 class. 71% of the students passed the first test. Of those that passed the first test, 73% passed the second test. What percent of the students passed both tests? Okay, well, let's see here. 71% passed the first test. That's sort of akin to the pink part up above, right? So we know the chances of passing the first test for both of these. And then it says, of those that passed the first test, there's that of those again. Well, that's giving you a conditional probability right there. They're saying of those that passed the first, given that they passed the first, 73% passed the second. So let me type that up. All right, I've color-coded this for you. So let's break down what we know. We know that the probability of passing the first is 0.71. That's that pink phrase. Then we know the probability of passing the second, given that we passed the first, is 0.73. That's that yellow phrase. And what they're asking about is the probability of passing both. That's a question mark. Well, but passing both means you passed both the first and the second. So we need to use the multiplication rule right here. We want the probability of passing the first times the probability of passing the second, given that we passed the first. Let me write that out. There. So probability of passing the first, always do the first event there first, times, and then what's the chances of the second event happening, given that we already have the first accounted for? Okay, well, let's see. Probability of passing the first is 0.71 times, I'll put that in parentheses, times the probability of passing the second given we passed the first. That was the yellow part, which is 0.73. So all we have to do is multiply these two numbers and we've got it. And it should be about 0.5183. Since they asked for a percentage, we could say 51.3% or 51.83% of students passed both tests. right? So there's the green part that we were looking for. And then we used the pink and the yellow parts that were given to find that green part. Like that. And just in case this is helpful to you, I actually went back up here and did the same thing with the first question. So we were given the green, passing both, and the pink, passing the first. We were looking for the yellow part, right? The percent that passed both, or passed the second test, given that they passed the first test. There. So we were looking for that bit at the end, which I didn't type up, sorry. So it's the percent of those who passed the first test also passed the second test, right? In other words, they passed the second test, given that they had already passed the first one.